So I'm happy to introduce Dr. Ed Generazio, who's our speaker for this month. Ed is with NASA Langley Research Center. He's a subject matter expert on non-destructive evaluation methods, or NDE methods, providing guidance to NASA personnel on NDE technical issues and policy, as well as serving as a NASA representative for NDE to other government agencies. Dr. Generazio has served as NASA's technical warrant holder for non-destructive evaluation, the NESC NDE chief engineer and discipline expert, the NDE branch head at Langley, and has served as the agency's NDE program manager for 2 decades. He holds a Bachelor of Science in Physics from the University of Massachusetts, an MS in Solid State Physics from Illinois Institute of Technology, and a PhD in Physics from Penn State University. Dr. Generazio has published over 100 publications and holds 13 patents and patent applications. And the subject of the talk today has to do with the electric field imaging inspection technology that Dr. Generazio developed. This method has been demonstrated to remotely characterize electric charge distributions, and the technology has a variety of possible applications in remote sensing of charge distributions in electric fields in both terrestrial and space applications, and that's going to be the subject of the presentation today. So I'm going to turn it over to Ed. I need to warn you before Ed gets started here, he's got a fairly long presentation. There's about 80 charts, so it may actually go over the hour we have scheduled. I think we'll just let Ed go ahead and give his presentation. I think if you have questions, why don't you ask them as they come up? And if you need to leave early, you can do that. But I think the topic is certainly of great interest to all of us, and so I'd like to give Ed his full time here, however long it takes to get through the charts. All right, Ed, so I'll turn over the floor to you.
Okay, thank you. I can get through the charts easily. I'll just give a heads up to some of the folks here that in the past I've given this presentation twice, but I've expanded it this last time, so you're going to get more, and that's why I have 80 charts. And the Q&A generally lasts much longer than the presentation when I'm done, so I'll just give you an idea. But everybody seems to stay awake, so with that I'm going to go ahead and go forward. The first chart, Missy, you got that up? It's just the title?
Yes, I do.
Okay.
I'm on the very first screen.
Yeah, okay, thanks. The reason I wanted to talk about this one to begin with is that the Senate director actually received a note that some of the universities would like to have wanted to indicate that they were part of my growth, and so now I put my universities on there at the bottom list. So I started off with my high school and worked the way up, so that's why I did that. So others that may see that in the future, that was very surprising to me to see that. So, okay, let's go on to the next chart. Where this came from, some time ago we had a fatal accident with aircraft, TWA 800, and it was found to be most likely due to wiring issue in fuel tank. And so Congress actually asked NASA specifically to look at inspection techniques for wiring. At the same time, we had the McDonald report coming out of the Space Shuttle program indicating that we've had several wiring faults and exceptions in the Space Shuttle. And so those two combined came down to the NDE program, and I was doing the NDE program management from headquarters. I reported to headquarters for the past 20 years in NDE for the agency on all the NDE issues. And so we started a wiring task to look at inspection of wiring. Out of that task came what you're going to see talk about what I'm going to talk about today. We were looking at there are a variety of ways to look at damage in wiring or aging in wiring. Some looked sniffers, some were vibrating the wiring, looking at faults that way, et cetera. I myself, as a branch head, I had no space, but I said I think what we really ought to look at is the electric field that's outside of the wire, because that's really what's dictating whether it was going to fail or not. So I set out to build an electric field sensor, and that's how this all started. And that was in 2002. That was sure just before we had the Columbia accident. And the next slide, slide 3, shows a FET array, a field effect transistors that I put together. I'm partial to FETs in the sense that I do a lot of electronics myself, but in my PhD work, I looked at building an amplifier to work in liquid helium to look at ultrasonic third sound at 1.3 Kelvin. And so on the upper right-hand image of that, you see one of the original FET-based amplifiers that I built, and I was actually able to get a FET to work at 1.3 Kelvin. And for me, that was a great success because it was very low Johnson noise in that case. I also worked on the absorption of free carriers, the carriers inside of the semiconductors, the absorption of light into by these free carriers when they're placed in the magnetic field, and that's what's shown on the left there. And the reason I put that up there is that I started to see the word KT in your document on Guide to Mitigating Spacecraft Charging Effects. And I said, oh, well, I use KT all the time when I was doing the second-order Born approximation. So I just put that up there to say that it has relevance to your work that you're doing in terms of space environment. And the lower right-hand side is some theory showing that these free carriers electrons will absorb in different state levels, and you can quantize those states in a magnetic field. That's not part of this work, but I just was trying to show you that I was familiar with FETs in some detail, or semiconductors in some detail, and that's why I used a FET in the first place. It's because I had some experience with it. If we go to slide 4, one of the configurations of a FET that I use is you see the D, S, and G. Those are the typical designations for drain, source, and gate of a FET. I tend to stick with bipolar FETs, so the drain and source labels can be flipped, and so don't worry about that. It just makes it easier for me that I don't have to keep track of the drain and source if I use a bipolar system, and that's what I've stuck with. The gate on this particular diagram I have here, this is an array of FETs. It's floating, and you would never use a FET with a floating gate. You always have some sort of protection mechanism. The gate is why the gate is always protected when electrostatic packaging, manufacturing, through the whole process, because the gate is very sensitive to electric fields, and so it has to be controlled. You don't want electric fields around it. I use that as the process. I said I want that high sensitivity so I can measure the electric potential, electric field in an environment. I want to take a risk, and so I leave the gates floating, and that was part of the original patent. It's that there is no other connector to the gate ever. And so, okay, so once I got that started and started working with gates, I'm going to speed up a little bit now. As I started working with gates, if you leave the gates floating in any environment, they tend to start charging. But also, it's not just the gate that charges. The entire system starts to charge. For instance, the packaging material that's around the gate, the support system that you have holding the FET up, etc. And so I just drew a picture, just a circle that goes around here, shows that there's a structure that's holding the FET system together. And how does it work? You change the potential on the gate, that's G, and that's the potential in space, for example. And then you get a change in the conductivity in the semiconductor area here, and you get an increased current flow. And from that, you can measure a voltage out. Those arrows show you're measuring a voltage out. So it changes high impedance on the gate side, low impedance on the data acquisition side. Let's go to figure 5. Whenever you now I've talked about gates, kind of give you the principle of the area that I was working. And whenever you put an object in an environment, in an electric field, in a uniform electric field, or non-uniform electric field for that matter, the object changes the original electric field. So if you were building a measurement system, you wanted to measure the true electric field, you have a tough time because whatever measurement system you use, you generally will distort the field. So this just shows you that all the materials generally have a dielectric constant or relative permittivity shown here as this epsilon. Put in an environment and the electric field is distorted depending. It either increases the electric field inside the material or decreases the electric field inside the material, and that's showing the top two. Or if it's a conductor, the electric field comes normal to the surface of the conductor, and the electric field is not inside the conductor. So basically what I want to show in this 5 chart, number chart from 5, is that no matter what you do, you're going to start distorting the field when you try to make a measurement system to measure the true electric field. There's one other element that you have to add to that. Now, whenever you touch something, there's a triboelectric affinity. If you touch something, for instance, I'll pick some numbers up here, mica glass, it tends to leave a positive charge. You end up with a positive charge on the surface of the glass. If you do something like Teflon, you touch Teflon, it tends to leave a negative charge. And the understanding is, I believe that this is not really the accurate way we should talk about triboelectric affinity in terms of touch, and you'll see that later on. I don't believe that's the right representation for it. There's very little science on triboelectric affinity, and there are some ways to measure that people have done and come up with a variety of different answers. and basically try to set standards. But what I wanted to point out is that with all these materials that I have listed here, or at chart 6, I'm sorry, all the materials I have here on chart 6 is the upper ones are positive, the lower ones leave a negative charge. But there's materials that are in the neutral area that if you touch them, they don't change charge. Charges don't stay there. And so if you start to build an electric field imaging system or measurement system for the electric field, if you start to use materials that have these areas that they're not affected by touch. By the way, everybody picks up the sensor, it moves it somewhere, or something moves it somewhere, so there's some operation going on, so you're always moving things around. It's good to have materials that have neutral triboelectric affinity and don't charge. So now here's the problem. I want to measure the electric field here, go to figure 7, chart 7. I want to measure the electric field at this point, I put a little star there, and whatever structure I put in there around there, it's going to distort the electric field, and I'm going to have a tough time trying to figure out. There are ways to try and back out, but it's usually so complex you can't get the true electric field that was there originally. But if you follow these 3 rules here, if you use a low dielectric constant, material with a low dielectric constant or a low electric susceptibility, if it's a non-conductor, and if it has neutral triboelectric affinity, that's on page 7, you're approaching the point where you can measure the true electric field. It becomes a catch-22 if you go to page chart 8. It becomes a chart 22 because the triboelectric affinities of materials and the dielectric constants are not known for every single material that you have, specific to the material that you're going to use. You can get some general numbers from a book of polyvinyl chloride, but it's not the answer that's on your system that you actually got from manufacturing. You actually have to test that. And how do you measure the dielectric constant of the material? Well, you end up with a catch-22. You don't know these constants. You need electric field imaging system, measurement system to actually get there, and you also need to know the triboelectric affinities, and how are you going to measure that? You got to measure the electric field coming from these systems. So you get a catch-22. So I say that now is because this is what I've been doing over the past few years, is going around in a circle, zooming in to the right way to get these measurements. The chart 9 shows a diagram of my original work where I used a wire and I had an array of sensors on the left. You see that this is just, I was learning one of the software packages for the electric image at the time, and I put an array of sensors in this object here that show lines, and you have the figure on the left. And through that measurement system, I ran a wire through it, and I kind of drew out what the electric potentials would look like if there is potential on the conductor. The conductor is the dark brown. Insulation material is red. The potential as you move away from the wire would be radially symmetric, and that's all I was looking for now. Now, remember, I'm trying to solve the problem because of TWA 800, not solve the problem, but look for a test system that could identify failing wires ahead of time. And so the idea was, if you look on the right, that there's a little damaged insulation, and how would the electric potential be around a wire for damaged insulation? That's how I expected that change in potential. I'm showing a V1, V2 being distorted in that right-hand figure on chart 9, that the electric field sensor would pick up that. By the way, the electric field at the gate measuring the potential, not the field. It's measuring the potential of the environment, not the electric field. You need to get the difference between 2 potential rings here, for example, on the left side, between V1 and V2, to find out what the electric field is in the radial direction, and similarly on the other side. And it would be distorted field on the other side. So let's go to chart 10. Chart 10 should have a video on the lower left, and it should start up by itself. But it's my first array that I built, and you'll see that the wire is changing its potential. And Missy, did it start showing the movie?
It does, yes.
Okay. What you're seeing is that the electric potential radially changing away from the wire. I just ran it through the array that I built. The array was actually meant to be a square array, and you'd use the other side, but I decided to just drill a hole through it and run the wire through it so I could show that I'm actually measuring the electric potential. And in that movie that's showing, you'll see that among the bottom, where it's on a support table, the table is actually affecting the electric field. And you see those LEDs that are lighting up. The lower LEDs are changing. That's because the structure is affecting the electric field that I'm trying to measure. So I need to move away from it. I need to change the structure that's holding the system. So this one kind of set me on the, let's go to the next picture. I built a prototype. I'm moving away from this at this point. I just showed that I could measure the electric field around a wire, and that's all I did with that system. Is I changed the potential on the wire. Comments came in, criticisms, I should say, came in. Well, who's going to use that on an aircraft? You know, who's going to run that along a wire and things like that? And I got tired of the issues. I said, okay, well, I'm just going to keep going, and I won't address it just for that wire. This was just my first run. And also, I put, if you notice, I put a in this particular image. We're on chart 11. Sorry, on chart 11, I was trying different ways to guide if I could change the direction of the electric field around the wire to be more radial, so I could get an exact answer. But we had the Columbia accident at that time. I don't know how to turn that ringing off on my phone, so we'll have to go somebody else's phone maybe. Okay, let's go to chart 12. Okay, now that I've got some confidence that I can see the potential with my gates, my setup and my arrays, I decided I'm going to build a real tall array, and we're on chart 12 now. And on the lower left there, you'll see E-sensor array. That's a long array of sensors. There's 192 of them. The sensor array originally was to be 8 feet tall because I wanted to do inspection of packages. I stopped at maybe 4 feet up because I got tired of wiring it. I used triboelectrically neutral materials, and what I did in that particular case, the E-sensor array is actually made out of balsa wood. So in my lab, I have an 8-foot piece of balsa wood that's holding all my sensors for this linear array. Okay, on the right side is a quasi-static generator. I'll show why that's important, because when you measure an electric field, I mentioned things charge. If you take that sensing system, and this is true for all sensing systems as far as I can tell, if you put them in electric field, the sensing system may make a measurement, but also the sensing system itself changes that environment, and it begins to charge itself. And so I decided that I need to back up that process, and I was thinking push the charges back into the system, push them back into the semiconductor, reverse the process of charging, and you can't write that out mathematically in the sense because you're working with structures, odd-shaped structures. You're working with semiconductor materials. You're working with packing materials that are holding the semiconductor. You're working with the wiring. You probably won't be able to do that in an analytic way. You're going to have to do it as a correlation or some process. Well, the process I use was I'm going to reverse the electric field on the measurement system every time I make a measurement. So this is actually on the far right, we're in chart 12, is a dipole that spins around. You're going to see a movie of that, hopefully. It's built out of triboelectric neutral materials around it. It's built out of wood. There are 2 poles to it. There's a positive and negative. It's basically a dual Van de Graaff generator that's floating. There's no wire connection to it at all. It's battery powered. And inside the Van de Graaff is run by a wireless micro helicopter motor. And it has the usual pulleys and things like that to move the charges around, to move them onto the electrodes. The electrodes are the 2 gray dots, gray circles on the left and right of the dipole. That dipole produces an electric field onto this plate, which is, you'll see an electric insulator plate there, an electric insulator, but next to the electric insulator, it's about the bottom lower right. And on the upper center, you'll see conducting electric potential surface. That blue surface is a floating surface, and when the electric field from the dipole attaches to it, or is normal to that surface, this plate becomes an equipotential. And in the near field approximation, and there are other ways to do it, but for the work that I'm doing, in a near field approximation, the electric field coming from that plate is uniform, and I can uniform enough, let's say it that way, that I can do inspections and I can look for distortions in that uniformity of that field. And that's what's showing here. I'm showing some lines going from right to left that is representing a uniform electric field going towards my sensors. And in between, you'll see an egg-shaped type of thing at the center of the figure in chart 12 is an object, and I'm going to look at the distortions from that object, distortions of the electric field from that object at the site of the sensor array. There's also a conveyor. You see the conveyor is blue down the center there. It moves in the X direction. Down below is the axis, by the way, here. Y is going vertical. Z is going to and from the sensing array to the plate, the electric equipotential plate. and let's see, X is coming towards you out of the chart. One other point I want to point about this conducting equipotential surface is that while this thing is rotating, this surface is changing its potential according to the orientation of the quasi-static generator. Okay, I'm going to come back to these signals, but just to show you take data from this, just like I showed the data acquisition system coming off of the array. There's a series of waveforms that you collect, and you can see they're a little bit oscillatory here, and that's because it's oscillating with the quasi-static generator. By quasi-static, I'm talking 2 or 3 hertz, and then from that information, you can measure the gate, the output from the sensor, and you can create an image. And from the image, you can eventually, if you calibrate it, you can find out what the electric potential is to create that image, and you can also correct the electric field. I just show electric field here, but that would take 2 steps. I did this for a patent, so I had to put the electric field image up here. But there's actually 2 steps, and I'm going to show you those 2 steps. Let's go to the 13th chart. And if you hover over, I guess it's going to start the lower right-hand blue image. You'll see this is the quasi-static generator. It's on chart 13. Missy, we okay?
Yes, we're good. Thank you.
Okay. It's rotating around. Above the rotating system it's rotating is the quasi-static generator. So you can see I put a big label on it so nobody can miss it. It takes a big space in the room. The copper panel that you're seeing was added later. The actual equipotential plate is on the other side facing the window to the far right. You can't see the equipotential plate. The vertical balsa wood piece that you may or may not be able to see next to the C in quasi-static goes above the letter C and goes up through the Phoenician blinds. That's the actual array of sensors over there. But, okay. The other images just shows the inside. It's a Van de Graaff. Upper left is just a Van de Graaff generator type of structure, and there's a positive and negative electrodes on that, and that's rotating around. Okay. I did get the patent for that, by the way. And let's go on to the next chart. This is what the data. This is the important part of the data. Chart 14. This is the response from those 16 of the electric field sensors. This is their output. They have equivalent, for instance, 16, and they're not overlaid because each FETs are notoriously for not having good characteristics between each other. It's very difficult to collect matching FETs. The process is very complex. The process to maintain the gate uniformly is not well controlled. It still isn't well controlled, so they have a wide variation in their nominal properties. And you're seeing that right here is that for these same FETs, which I'm not going to claim them to be matching at this point because I did not know that I had to have them matching yet. And it may or may not be necessary, and you'll see why, that I can get excellent data with this particular FET. That there's the peak and their minimums. And every peak is where an equilibrium point is. If I turn the generator off, these all turn into straight lines, and the straight lines will be at the height, the voltages. On the left, you'll see a 4.5 volt for the blue line. That'll be a straight line going across, and that's the equilibrium potential of the FET in the environment that it's at and with it charged the way it is. So I call that the equilibrium potential. I'll show you some of those when they stop later on. But what I wanted to show here is it's rotating around. Every time it rotates around, I take an acquisition point where the strongest field has occurred, and I'm showing the word acquisition point. Now that's not just the lowest point. It's where the orientation of the dipole is exactly that the field is exactly lined up with the sensing array. Okay, it's not the minimum of the waveform that you're seeing. It's a physical orientation of the dipole. So it may or may not be the minimum. The important part here is it's not a sinusoidal wave. And what happens is if you look at the upper part of all those curves, those are 16 sensors, by the way. The rotation rate is 2 hertz here. 16 sensors. The upper part is non-sinusoidal. And the main reason it's non-sinusoidal is that's where it's starting to charge. And so you'll see a slight tilt in it. If you slow it down, it will never get to the acquisition. You'll never have deep acquisition points for taking it'll never make a measurement. It'll always charge the sensor, and you won't see the correct result. And so if you have it running properly, you'll have a sinusoidal, sinusoidal type waveform that's uniform on the top and the bottom for when there's no sample present. I got to be careful. This is for no sample present. So anyway, the top flattened parts of those curves are an indication that it's charging, and the quasi-static generator is not going fast enough. Let's go to the next slide, 15. I used that system for the first time in, let's see, I got my first image in upper left-hand corner in January 2012. That was my first image of an object, and you can see it's kind of weird looking, but it was a pear-shaped object. Let me say it that way. I'll talk more about it. I was so excited that I got an image. I stuck myself in the machine and stood on the conveyor belt, and this is a self-portrait. We're in chart 15. The vertical lines, you'll see some vertical hashing in there. That's because I thought that the dipole had to stay running all the time while I was making a measurement. So I had the thing spinning around at 3 hertz, but I also internally I had the Van de Graaff generator running at a high speed to maintain a high potential. And I didn't know what the potential I needed either. So the vertical lines are the changes in velocity, changes in the speed of the Teflon and the rubber belts that are going on as it's rotating around. If you can imagine the system that is here, it's squeaking. I've since found out that I don't need to keep that generator running. I can just turn it on, I can charge them up, and I can use the system for hours without recharging it. And it runs off a 7-volt battery, very small 7-volt battery. So I can get a day of use out of a very small charge in the morning and just have a uniform potential most of the day. And it depends on the day, and I'll talk more about that. Okay, that's the vertical lines. Horizontal lines are differences in the calibration between each of the sensors. From the top to the bottom, there are 192 sensors. And you're going to see how well you can calibrate those sensors just as they are. So you don't have to have match. You just have to be good at calibrating. And your dimensions there, you can see there's only 36 inches. And since I got this image, I went over, I quickly got some software. This is just Adobe Photoshop, and I did some simple image processing, canned packages. It's not meant on the right. It's not meant to be a physics-based rendition or representation of anything other than it was a Photoshop option that came out. And when I looked at it, I did have a cut-off shirt that day. I had all cotton clothes on, except I had polymer socks. And you're going to see at the bottom there, you're going to see at my ankles area, you see that it's different. And that's very important because I didn't know at the time what it was. I just said, oh, this is great, I can see stuff. I'll show you later on what that is, why the polymer socks are showing up in that manner. Because I started out in the NDE area in this electric field imaging, I decided I better go get some composite specimens. And so I got a composite compression test specimen, which is, we're on chart 16. Go to chart 16. And this is a compression test specimen. It has a honeycomb, and it has composite material in the front and back, and it's been crushed slightly. So there are cracks in the front and the back, and I used that as my first material test specimen in my system. I did an electric potential image of that, and you can see that I also learned how to calibrate just software, the sensors, if I may match up the equilibrium point in the minimums so that they're all uniform, and I can use a linear calibration between these for all the 192 sensors. It works out very well, and there's more fine tuning that you can do. But anyway, this is the electric potential from that system. You can see, first of all, you want to notice that the above in B, and the top third, you see it's a very uniform electric potential away from the specimen. As you go near the specimen, you see that it gets darker first, and that means that the electric potential has increased, not decreased. And then as you get to the support brackets, which are, if you look at the optical images, which are at the top, those are the support brackets that they put it to clamp on, that the support brackets had a very low potential. The potential dropped in that area. And then if you can see it in your figures there, you'll actually see a line through in figure B. You'll see a light line through the center of the specimen. That represents the crack. I'll show a little bit more on that. So basically, you have a uniform potential away from the specimen. As you approach it, it gets to be high potential, and then it drops to a low potential very strongly. That's the best way to say that. I was reading some of the documents you had about the way to measure, how to make that statement, but it becomes a very low potential at those brackets. And the right side, the 3D, I tried to get fancy with it, so I did some 3D renditions from the same software package. And basically, it reminded me, and I tried to use this as a explanation to everybody. It looks like as if somebody had a balloon blown up and they pushed their fingers into it, and you're getting these sharp spikes, but the balloon is pushing out between your fingers. It's pushing past it. And so I was just trying to explain that. That's what I'm trying to show in this 3D image in this 3D 45. This is this increase in potential outside the object and a decrease. And so, okay, let's carry on. That's just the electric potential, and it just it's not calibrated here. I'm just looking at the output from the sensors. You can let's go to chart 17, and I'm going to speed up a little bit now. You can do that away from the specimen and near the specimen. Take two images. You move one. You take two images from that array. You scan it twice, and once you have that information, if you register everything properly, again, chart 17, you can get the X component, the Y component, and the Z component of the electric field. You can get that just from a simple scan along using the conveyor belt, but if you do it away in front, if you get an electric potential near and far from the object, you get the Z component. From that, you can get the electric field magnitude shown over there on the right-hand side where it says positive. And you can see right around the edge of the support brackets, you have the light here represents strongest electric field. So you're seeing that the strongest electric field is coming from the edges of the support bracket, and also you may be able to see that there is also electric field lines going horizontally in the center where the test specimen was cracked, both in the front and the back. You can barely see it. I was still working with it, and the math for determining the electric field from the electric potential is shown above on the upper right. The inverse is just the inverse of the photo of the image. Nothing special about that. So basically,
quick question: how long does it take to obtain a sequence of images, the X, Y, and Z?
You can do them at any speed, and that just gives you your resolution. In other words, I've done one in say 30 seconds. I'm going to show you a two-dimensional array which does it instantaneous.
Oh, okay.
Okay. I'm going to get there if I get there in time. But that was one of my frustrations with the 1D array, is that I had to wait, and I had to I have my quasi-static generator spinning around. And if anybody, I'll add to this, if anybody happens to walk into my room, their potential affects my measurement because now they've changed the environment. So I had to be careful about how I take the data and when I take the data. So there's some rules that you have to keep track of. But I'm going to show you a 2D array on that, so you can get real-time information. You can go a little bit further. I haven't published this, but you can actually generate it. Since you know this electric field magnitude positive, that's actually that's just the magnitude. You also have all the vector components that created that image, which means you can now project where the electric field is coming from or going to, subject to the constraints of the dielectric properties between the environment and that system. So if it's a complex environment, you have to include models of that environment where it's coming from. But it's a simple environment, you can backtrack into the system. I'm going to show you an example of that later also. So you can actually do some focusing, and I tried to focus in to see the cracks a little bit better, but all I got was this focusing images that you see here, which are kind of trying to show that there's some maybe some damage in the center of it. It's not clear to me. So I'm just wanted to point out that you have these vectors now of where the electric field is coming from, and you can use those as projections just like a microscope or a telescope. You can project down where these things are coming from, subject to the constraint of, I'm on chart 18, by the way. Go to chart 19. Subject to the constraint that you know the dielectric properties of the system that you're imaging. Say it that way. Let's go to 19. Now again, I'm still trying to learn how to build systems. We're on chart 19. I looked at a cable, RG174, because I was trying to figure out what's the best way to connect these things, and I want to do more now. And I put a RG cable in my system, and I actually imaged that cable itself. And 100 centimeters away from the cable, I'm seeing large changes in the electric field around it. I also put a LM34. I know nobody uses dip circuits anymore, but I still do and had one, and I used the dip circuit. I put it in on the holder. I held it up with a small piece of wood at an angle, and I can show that the electric field, the electric potential is changed just to the presence of the dip itself. So when you build your electric field imaging system, you don't want to have these wires and you don't want to have your electric circuits near the fields that you want to measure. So that adds to your knowledge of how to build a better field measurement system, electric potential and electric field measurements. Let's go to chart 20. I did get through the guide to mitigating spacecraft charging effects by Henry Garrett and Albert Whittlesey. Thank you, Stephen Goods. I think I got the name right. He forwarded some information to me, and what I put this chart up. This is a chart from that one of those pages. Hopefully, I put the reference. Yeah, I do have the reference. I have their reference, but I'm using the same voltages that you've been talking about in that document. My generator is 100,000 volts. I'm using the safe. It's human safe because I'm using the equal potential plane that's not. It's not connected to a direct current, so there's no chance of little chance of human damage. I guess that's the best way to say it. Low arcing capability at low current. It would have microamps off of it, so it's safe in that sense. But anyway, I'm using the similar voltages that you have in space, and I didn't know what these voltages were, so it was nice to see that. Okay, now that I've shown you that I put a wire in there and I could see it in effect, I said, well, what about the insulation? If I want to use a wire, what kind of insulation should I use around these? So I took a magnet, number 38 magnet wire, and I put a section head polyvinyl chloride, cotton. I left some of it blank, going from chart 20. I left some of it blank, no insulation on it, some rayon and polyethylene, and I imaged that system, and you can see the length. It was 24 inches long. And I got large changes in the potential due to the insulation materials. So actually, I settled on number 38 magnet wire as a good wire that doesn't affect the electric field sufficiently a lot for what I'm working with. Now, if you go down to something, you start to look at micron systems and things like that, you're going to have to change that wire out. But for what I'm looking at, the number 38 magnet wire alone is adequate. It's not going to disturb my field too much compared to these other materials that I just listed. Now, another point that was in this image that I didn't recognize at the time is if you look at the polyethylene and the polyvinyl chloride, there's a shadow on the right on both of them. I'm sorry, there's a shadow on the right in both of them. But if you look at the cotton and rayon, there's some shadowing on the left side. And I didn't know what that was from, and that led to the next work. If you go to 21, I took some Teflon, acrylic, wood, nylon. I bought rods, identical rods, all 1 inch diameter, solid rods. Garolite, which is the old Bakelite, Garolite, mica, ceramic, borosilicate glass, and copper and polyester. And I stuck them all in a row, and I ran them all through the machine. And this would have been on one of those longer runs where I ran it for 5 minutes, for instance, took data through the linear array. And you can see chart 21. The as-received rods, this is what the image looked like. If you look at that's the image that I would get. That's an image of potential. And what I want to point out in this is that the copper rod, which is the second from the right, had such a dramatic effect on the potential that, and you notice it's all dark around that side, but the left side of the image is all light. Well, the electric field, the copper rod, the second rod, might modify the electric field so much it affected the measurements on all the others. I pulled the copper rod out down below. Let's see. I'm sorry, didn't pull it out on that one. Sorry, take that back. I did take the copper rod. Just so you know, I did take the copper rod out, and that disappears. But what I did do is, after I did this image as received rods, is I took a silk cloth and I passed it across all of them just once. And these rods, they were about 1 foot tall. And when I imaged it again, I got the bottom image. And I didn't understand fully what was going on, but I did at the same time. There's one sub-story here that folks didn't want. When I wrote the publication up, they didn't want me included, so I forget to tell it. But when I put these rods in, when I put the Teflon rod in the first time and I did this top image, the Teflon rod on the far left, where I pushed it down by hand into the wood holder, when I did this imaging, it lit up like a light bulb. It was like a lighthouse. The Teflon looked like a lighthouse. And from there, I didn't know what it was. My system had never given me any erroneous results ever from my experience. So to get this light bulb look there look at that time was pretty dramatic. Where did it come from? Well, it didn't take too long for me to realize because I touched the Teflon in the time between making the measurement, and I put insert it, and then I took the measurement, so there was charges from me touching the Teflon, and that led to me passing the silk cloth along all these surfaces. And these are all triboelectrically charged, and that's what happens just from that if you re-image it. So triboelectric charged objects will give you an anomalous, an added feature. Let's say it that way, added feature. And if I won't go into it deeper because I'm only in chart 21, but the shadowing on each of these are different depending on the same what I was talking about, whether it's as a negative triboelectric affinity or a positive triboelectric affinity. Okay, let's go to chart 22. Now that I know that some charging is occurring, I decided to take a Teflon panel on chart 22, and I wrote NASA on the front of it. And this is a 1 foot by 1 foot panel held in a wood frame. I wrote NASA, and I imaged it, and I overlaid the image so you can see where the image in the upper part there, upper middle, is the letters NASA, and the last A you can't see because it was saturated. And then I ran into a problem immediately is because I didn't know how to get rid of the words NASA. This was done by a finger, just putting the finger on Teflon, writing the letters NASA. I tried to erase it with a variety. I used aluminum foil. It was grounded. I tried all sorts of stuff. All I ended up with double and triple exposures of whatever I did every time I imaged it. So I went out and bought a deionizing gun and to erase it. And I learned that's how I learned to erase charges off the surface. Everybody knows how to do it, but I didn't know it was going to be a problem. So now I can erase. I've learned how to erase. It's going to be very important because I have a special in there for the space folks coming up. Is that I decided, can I see through on the other side of the Teflon? So I wrote the letter N on one side, and then I wrote the letter N on the other side, but above it. And that's showing at the bottom middle here. I'm sorry, the drawing on the far right, lower right, is how I did the ends, and the electric potential image is the result from it. So the system can see the charges on the subsurface coming through on the other side. Now, it's not, that field is obviously interacting with the dielectric material, and then it's coming out on the other side. So it's distorted to some extent, depending on dielectric material. But for me, it means that even though I would have erased just one side, I have to erase the other side also. Let's go to that's chart 22. Let's go to chart 23. Okay, I wanted to get back into NDE. I'm kind of playing around trying to understand charges here. And what's doing to my electric fields is I decided, well, can I use this charging to charge up objects inside a container? And let's go to chart 24. And this is going to look very similar to your the folks space things where you have the charging inside of objects occurring due to relativistic particles coming in and knocking off electrons, etc., and charging your objects inside of containers. And so I said, well, I looked at this, I said, oh, you folks have the similar issue, but my idea was I would take, in the upper left, I would apply an electric field, I'd put an object in the middle of it showing in B, I would let it charge up inside, I would pull the field away, and then I'd look at residual charges and see if there's any distortions, because those charges won't be able to move fast enough to get out, depending on materials, and I'd be able to see something. I didn't do too much in the area after that because guns were a big issue, and additive manufacturing came to NDE in a big way because we're making engines out of these materials now, and so we need to address that. I'm going to show you as I go to 25. As I looked at that problem and how to do it, I decided I need to learn how I'm going to apply this electric field. Chart 25 is, how do I do it for time? 46, oh, I better really speed, no, 46 minutes, I better speed up. I applied electric field to these spheres, and they have a uniform potential on them, but they were placed at different distances from the Teflon panel. And I just used the door to adjust the height, and I was able to apply a potential to those spheres, and I was able to write to the lower left. I go to chart 26. On the lower left, you'll see that I was able to write to the Teflon without touching it with my electric field. And after I erased it, I found out I could see a label on the back side. You'll see on the right-hand side there. and I'm going to show you the hardware on that in a second, what that label was. But I want to return your attention to the far right in chart 26. This is one of the things that I didn't do anything with. I saved it, and the file name was after front and back erasure, more data showed up. In other words, I created these writes on the Dielectric on the Teflon, but after I erased the whole thing, I ran it back through my system. This image came up. I didn't understand it. I filed it that way, but now I believe that the charges were stored inside of the Teflon, or some other event occurred that recreated. And if you look at that image long enough, you'll find out that there are multiple images of spheres inside of that image, and also my system reacted funny, and I wrote them as arc events because I hadn't seen these spikes, the vertical line in that far right. That was about a 75K write onto Teflon, and then erased. That Teflon was then erased back and front, but I was still able to image something on that Teflon, so I'll just pass that. This is what was on the back of that. That label showed up. That's that label there. It's in the center. I'm sorry. Go to chart 27. That's the label that created that mark on the back that became charged. I went from there. I was just talking about that. I went into materials systems, and let me go a little faster here. I put an ABS gun, no metallic content inside a container. I was able to image that potential of that gun. You can also see the fingerprints around the gun where it was placed. I believe that was the fingers touching the foam as it was being placed. I have to be careful I said that. I did not prove that, but that is the gun, image of the potential of the gun inside the container. And by the way, that was done 24 hours after the gun was placed in the container.
Are you on chart 28?
I'm sorry, that's on chart 28. Yep, that's an image of the gun inside a container. And I believe the little dots outside are the fingers that touch the images of the charges left by the fingers touching the foam as it was placed in the container. If you go to chart 29, I got carried away. I said, well, if I can do that, can I do any forensics for people walking across rugs? And I had somebody walk across my rug. I had to change my system to do this because I can't use a quasi-static generator. I actually cut the rug off the floor. Don't tell anybody at NASA. And I lined it up and put it in my quasi-static generator, and I was able to image the footprints, and if you look carefully, you'll see the tread marks in the image of the treads of the shoe, and that's the actual shoe that did it. I thank my office neighbor across the hall. This is some data on, I'm going to go to chart 30. Just quickly, I'm going to get back to this, but I was trying to get some sensitivity measurements, and I ended up with 1.55 millivolts per centimeter. I believe I'm 3 orders of magnitude better than that, since this is very old at this point. But I was just doing it from a finger scratching head and 1 centimeter from the body. So this number is TBD. It's just been getting better each time, and I want to get to the other images. So let's see. Ephemeral sensor. I put the sensor and I started rotating it instead of leaving it fixed. I said, let me rotate the sensor and do the opposite of the quasi-static generator. I'll put the field on the opposite direction on the gate for the FET. Repeatedly, I'll rotate it around at a quasi-static frequency. I was able to do that, and I end up with similar type of processes as it rotates around. Go to chart, I'm sorry, that was chart 32. That's just a diagram from the patent to rotate the sensor around. Chart 33 shows the potential. The blue line is the potential that it's measuring the rotating sensor going at 2.4 hertz. The upper image is with no object in place, but it's no object present, and it's rotating around. Each peak is 360 degrees, and when an object is present, you can see that the potential is dropping. And I'm just showing where I'm making the measurements for every time it rotates around. Well, that was a gold mine, because that allowed me to remove, go to chart 2034, that allowed me to remove the error in the measurement due to charging of the gate and the structural system that's around the gate. And then the upper image shows the non-rotating sensor. This is done simultaneously, a rotating sensor and a non-rotating sensor on the same object passing down. They were placed on, the sensor was placed on a conveyor belt. I'm sorry, the object was placed on the conveyor belt, so I'm imaging a cylindrically metric object. And if I don't rotate the sensor, I end up with the upper figure, and that dip below the equilibrium, that's an indication that the gate is charging. When I have a rotating sensor, I have a nice curve showing lots of symmetry. It also had a gain that was 10 times greater than the non-rotating one. So gate charging causes a decrease in the sensitivity just by the process of gate charging, and I say other charging too, the system charging. Rotating the sensor gets rid of that, and you end up with this nice. And I've done some modeling, and you can pretty much get that to match the model of a charged cylinder. When you do modeling, there are always lots of free parameters, and I can get it to match within 2%. But I did not focus on the modeling. I was focusing on the symmetry of the system, but I just wanted to say that you can get that to match up adequately to start with. I did not pursue it further to go on to chart 35. I'm going to go to solid state. I have to speed up here. Joe, am I doing okay?
Yeah, you're fine. Keep going.
Okay. I decided now that I understand the rotating the sensor, I said, can I build a solid state one so that I can pull the charges back off the gate and the structure back into the system, get them into the current flow, and I'm basically cheating. So I modified the FET, and I added this extra. I'm on chart 36. I added an extra potential to the FET. So I called it an erg FET at the time, but basically I'm trying to control the depletion layer myself here so that I can get rid of those charges by pulling them back into the system. If you go to charge 37, that's what the erg FET looked like. And I call it an equilibrium pump that I put on it. And chart 38 shows the circuitry that I worked with. I'm only going to go quickly through this because this one didn't work as well as I wanted it to. It worked, but it didn't work as well. But basically, it's just a circuit that I can change the potential on that equilibrium pump electrode quasi-statically. But I also found out that I could change the potential on the drain and source quasi-statically and do not the same thing, but a very similar thing in that process. So I was just playing around with the FET, the best way to do it. So I sent that in as a patent to go forward. It also had the chart 39 just shows a test setup for putting an object between an erg FET and a non-erg FET. The non-erg FET would be my original one, and the erg FET was the one I just showed you, where I'm going to put a pump on it. I'm going to pump the system, add my own potential outside the gate, and I'll go quickly over this. But I can get a very similar result to the rotating system.
We're on chart 39. I think Misty may be a couple behind.
Okay, go to chart 40. Yep. That's what the results come from chart 39. Taking the data, just using a conveyor belt again to move the cylindrically symmetric object. And the non-erg FET sensor above showing you're seeing the leakage effect on the upper right. If I use the erg FET center where I'm pumping that voltage, and the data is shown on the lower left with the pump, and the result electrostatic potential measured is shown on the right. And again, I'm going after just the symmetry. I've got symmetry again on my measurement. It was a cylindrical symmetric object. So I think this will work well, but it was not as sensitive as I thought it was going to be. Let's go to the next chart, 40. That's just what the data looks like. As you increase, going from left to right, I'm increasing the potential on the erg FET while it's being pumped, plus or minus 15 volts. You can see that it's the lower curve. That's the pumping voltage. I'm actually going plus and minus over that added gate. And I can do that because I added the gate. It's not part of their gate. I've got the gate just outside the system. And as you increase the potential, you get a decreased measurement of the potential. And from that, you can calibrate to your potential that you're measuring. Okay. I'm going to skip some here. Well, I just tried to show that I was trying to see if when I draw a line on Teflon, does it grow? Chart 42. I was trying to see if I draw a line on Teflon, does that line disappear uniformly downward in intensity, or does it spread out? Because I was trying to figure out how to do some designs. And what I have right now is that the charge distribution on chart 42, it appears to get wider as it's decreasing in magnitude as a function of time. It went up to, 10 minutes I think I had on here. I measured that. I repeatedly measured that singular line, which was hand-drawn by a finger on Teflon, with the erg FET. I was able to see that it's most likely to be broadening in terms of width. The line is actually getting wider. Let's go to 43. Okay. I'm tired of doing lines and trying to reconstruct things. I want to see things in real time, so I built a 2D array. We can go over that. It's spaghetti wiring for me. I know how to do it, but I learned a lot through the process. I use canned stuff. This is to go to 44, chart 44. Shows the 2D array. It's in front of the quasi-static generator there on the right, and that's an image of it. Just sitting there, upper left, shows all the waveforms. I had to get a big screen TV because I couldn't see all of them on my little screen, so I put a big screen TV in. And also I had since I know that how they construct the arrays and supports, it affects my measurement system, so I had to make a special platform for it where they wouldn't touch it with any oils and things like that. And they're showing me that they're using all cotton gloves when they handled it and packed it in paper, and they didn't allow any tape on it and things like that, so they're being very good. On the right, you'll see the 2D array, but I'll point out that I broke down and I used those wires, which with the silicon outside, which would be a big no for electric field imaging, but I was desperate to see the results in real time, so I went ahead with it. They can be replaced with other wires. It's just that I ordered that because they would make them for me, and so I did it. But so those actually need to be removed and replaced with cotton-covered wires or some other type of magnet wire system. I did it for speed. Very far upper right, you'll see a color image. That's the image of the output of the system. Let's go to chart 45. And if you go, while I was building the array, serious concern came in about being able to detect active electronics in containers. And they asked me if I could do that. So I took a strobe light, go to chart 44, and if you put the mouse over the video image on the far right, start it up. Missy?
I'm sorry, on what chart?
Back up, chart 45. On the right-hand side, there's an image.
Okay, it's running.
Running. Okay. I'm going to run at the same time. Whoops. I bought a strobe. I put it in front of my array. This is an older array. I was still building it when I was working on it, and I had the strobe light up 6 times in a row. It's its own system that would do that. And this is the image you see. The electric potential, dark is high potential, low is light. It turns lighter in this case. I was still learning how to do the displays. This is the black and white, and that's all it does on that. So okay. I tried different woods. You'll notice there's lignum. You won't notice that, but there's lignum vita wood, the dark green. There's also balsa wood. I put the balsa wood in front of it because I didn't know if the 300 volts in the strobe light would affect my sensor. Let's go to chart 46. This is This is the results, the data from 2 sensors of that array. I just took 2. They're not overlaid. They're separated a little bit. That's their natural separation, by the way. I didn't go back and calibrate those. And you'll see that there's a change in potential for each strobe. Each lighting of the strobe is a minimum there, and you can see where it charged up each time. And you can also see why the company only allowed 6 flashes in a row at that frequency because they can't charge it up fast enough anymore. So that's what's going on in there. This is over a period of 0.8 of a second. So that's what's going on, and you can see, go to chart 47. You can actually identify which elements are active in the circuit, and this is 60 milliseconds apart. You can actually track what's going on, and this is remote. This is remote, and you're seeing inside of a container. And also, I have my array behind a piece of balsa wood, so I'm protecting my balsa wood, and I'm seeing through the container, which is polymer system. Let's go to chart 48. Further concerns came in about in this area, so I imaged a high voltage circuit. If we go to 48, you'll see a dark blotch. The circuit that I imaged is down at the bottom. You'll see some wires and stuff in that black area. It's got blue, yellow. That's the actual circuit. It's about 4,000 volts, run off a 12-volt battery. They wanted to know if we could see some activity inside of a container, basically. And that's what was imaged out. And the electric potential image is shown above of that actual system. I'm going to show you an overlay so you can see where it sits shortly. But what I wanted to point out is it also saw these AC waves, electric field sensor. I focused on low frequency, static, quasi-static. I tried to stay away from electrodynamic. However, the FETs will go up to gigahertz and much more. So you actually see all that information if you want it. So you just turn your filter off, and you can see everything at the high frequencies also. And this just shows that there's a high frequency transmission coming out of this box at roughly, I'll say 45-degree angle, but at an angle. And let's go to chart 49. It shows an overlay of the electric potential image over the electric circuit that was just imaged. In the dark area on the electric potential is the active area, an active area of the circuits that were there. And the bands that are gray that are going across, those are just calibration issues that I had not fully calibrated sensor to sensors going vertically on the system. Let's go to chart 50. That's just a zoom in on what's happening. You can see the AC signals coming from that object, and you can also see the dark DC static signal and the high voltage signal, which is the dark blotch in the center circle. And this was done, this is about 4 inches from the sensor. I'll point out that the sensors were overloaded with this particular object, and objects of this type, they're very sensitive to it. So they look like a bright light. If you put your bright light right in front of your camera up to a light bulb and took a picture, they're so sensitive that you have to back away from it. Okay, let's go to chart 51. We're going to now hit the area of interest of the area right there, electric field imaging of plasmas. I didn't know where to get a plasma or anything like that, so I went to go to chart 52, and I decided there was some concerns from outside that were interested in flames. So I said, okay, well, maybe can I image flames and what's going on in flames? And I found out the flames were also a plasma, and this, according to this chart. And so I focused on that. And we're going to show a movie here. Before I did that, I tried a match head, and just show one image. Go to chart 54. I did a match head, but there was so much sputtering off of the match head, I didn't want to damage my electric field, my 2D array, which I spent all this time building. So I went to an electric handheld lighter, the electric lighters that you use. So if we go to chart 55 and go to 56, chart 56 should be a movie, and I think it starts. You have to start it.
It's running.
So I'm going to hold a lighter about an inch away from my system, my 2D array, and I'm going to move the lighter around, and you're going to see the output from that, from the gases coming from that lighter. This is the ignition starting. You see that dark is low potential, so it's then it ignited, and that's the flame area. I don't know if it's the physical flame, but it's the charges from the flame. And I'm getting more careful on how I state this. I thought maybe there may have been a temperature effect, but so later on I put a thermocouple in the middle of my system and measured the temperature, change in potential due to temperature, but that goes in the opposite direction. It would be darker, not lighter. So this particular flame has a lower potential, that's the right way, higher potential than, it has a higher potential than the lighter itself when it's being started. You're going to see it's going to do it again. Hold on, I'm going to start it up. And what I'm going to point out later on, if you haven't gotten there yet, is there are extinction rings that show up. You're going to see it 3 times. By the way, all the modeling in the background, those are different sensors. I was just learning now a new issue. I have to learn how to calibrate sensors so that they have a uniform image. This is black and white also, and you probably have seen the extinction rings now. It's going to show them, I think, 3 times. So, and for me, that was something new. Ignition and extinction ring. The upper flashing, you'll see. This is where I did. I show a graph. You probably see that now. I can't see what you're seeing, but there's a graph showing the data to show that the temperature, that the potential goes in the opposite direction. The flashing sensors were bad sensors at the time, and I hadn't replaced them because I'm still learning how to use the system. I didn't know what a bad sensor was until I started identifying the flashing sensors. They either turn dark or fully on, or they flash like that. So there's 3. Okay, let's go to chart 57. Now that that was my first plasma, I said, well, why can't I use the ion gun, the plasma from the ion gun? So I took the ion, go to chart 58. This just shows the alignment. I have a different wood. I changed woods around my array to balsa wood, so now it's entirely balsa wood, and it's stitched together with rawhide, basically. You can see that around the perimeter. And I'm using an ion gun head in front of that array, and I'm going to the next. Let's see, the next image. Go to chart 49. The next chart, which is chart 59, and you may have to start that one also. You go over and click on it.
It's running.
Okay, thank you. So the upper right, the upper lowest potential is where the gun is and it's operating. And this plasma flow pattern, you can barely see it, and I didn't focus on, I'm not into graphics and stuff like that, but everybody says I should subtract the mean or average and come up with some signal averaging in this, but I haven't gotten that far. I got complaints that I should be doing color, so I'm going to go into color next. But I think you can see that you're seeing some flow coming from that gun, and so it's starting to see the potential in the plasma. Okay, that just continues like that, and so let's, all right, if that ended, Missy, let's go on to the next chart. And so we go to chart 60. Now I'm going to look at real-time. Now that I've seen plasmas, and I have some concepts of how triboelectric properties are affecting an electric field, I decided that I should be able to generate an electric field inside my system just by vibrating it, or in this, it could be by using phonons. Since I did free carrier absorption with phonons, I use the word phonons, which is what we really should be using, but it's vibrations or phonons. To separate materials, when you separate a material, two surfaces, separate them apart, I should be able to get the triboelectric properties to generate a dipole. If you go to the chart 61, I kind of did that graphically. If I take two materials on the upper left that are touching each other, and these, technically, they should be dissimilar, but it most likely will occur with similar materials also because they're not uniformly separate. They're not atomically flat. If you separate those using a phonon, you can generate, the charges will separate just like we saw with the triboelectric affinities, that you get a plus and minus charge distribution, and from that you get a dipole shown in the bottom of chart 61. If I create a dipole inside of a system, that will create a large electric field that will come out of the system if it's not a conductor, and I should be able to see that electric field using an electric field imaging system, or changes in electric potential. So if you go to chart 62, that shows different symmetric and anti-symmetric ways to create that field. Now you're coming from a neutral system now. You're basically creating dipoles out of nothing. That's what's happening here. And there's some data here showing I actually chose a sensor, which is I set it to 0 at this point for this display. But when I turn on the phonons between two materials, I'm going to show you that as an example. I get an oscillating dipole, and you can see that it's going above and below that 0 when it's turned on. So if we go, that's chart 62. We go to chart 63, and let's see, and that one turns on. You may have to turn it on, or it may turn on itself. But this is an image. I'm using my famous gun now. I'm going to try and identify the gun by vibrating the gun with using phonons. So it's in this container. That's where it's located. See where it's located. I'm in color image now because my neighbors wanted color at the 4x6 imaging array. I'm introducing phonons, and in the background you see some shaking, some changes in the colors, the shading. And that's a change in the potential due to the phonons that I introduced. And there's a little gap here, time. Again, you see some modeling, but I've got rid of some of it. And as I'm actually changing FETs all the time I'm doing this, I'm going in and changing some out and getting some better FETs that match better. You see it flashing. I didn't have sound on in this case. But in this case, it sounds like a vibrating sound. I did use a cell phone, basically a cell phone vibrator. And at the end, you'll see the object and the phonon image of that electric potential of phonon-generated dipoles at the very end of that image. The reason you don't see the whole gun barrel is because the gun barrel is not touching anything on that from the tip to the, as it goes toward the center of the optical image, it actually goes down into a quarter inch, so there's nothing touching the gun barrel on that surface, and so you only see the tip of it on the when it's generating the dipoles. Okay, let's go to chart 64. Now I've done all that, it's just go to 65. I decided I could make a 3D imaging array, and this was just a concept. I was trying to capture some areas in patents. And let's go to 65. It just shows different configurations you could use. Okay, let's go. This is a really good one. I love this one. But I decided, well, let me go to. I really want the electric field real time. I don't want the electric. I like the electric potential real time, but I want the electric field real time. So you can see how I'm going through this process. Now let's go to chart 67. I decided I could use the ephemeral sensor. If I put two of them in a rotating system, I should be able to get the electric field at a point in real time or near real time. So I developed 67. I call it Tian Mu after the Chinese goddess of lightning. And I did this not too long ago. There's a date up there in the upper left on chart 67. And I'm basically V0. I'm measuring the voltage here in the space, and V1. These two positions with this system. And again, these voltages in reference to the FET. And the FETs are all being run off of batteries, by the way, and they're all take 9 volts to run. So I'm measuring the voltage here and I'm measuring here, and then I'm going to spin this thing around, and I know the distance between the two, and if I have these two potentials here, I have it calibrated, then I have the electric field at the center point in the image. You'll see where the rotation system is. So on the far right, it'd be the top of the brown rod there. I would have the electric field. And if it's rotating around, I'll get the electric. I'm looking at the electric field from all different directions, and let's say the XY plane should be the rotation plane. And so let's take a look. Let's go to 68. I'm going to show two movies. This one is I'm going to show a little bit of it so you can get a flavor for what's going on. And then I'm going to show you a high-speed one over a period of hours. I was not able to do it before, during, and after a storm because when I come into the room to turn it on, I affect the sensing system. And I would also have to wake up in the middle of the night and come to NASA to turn it on. And the IT people were not able to get me to set it up so I could turn it on from home easily for a storm. So I'm at that point right now. And so, okay, let's go to chart 68. And that's a movie. If you turn that on, Missy, let me know when it starts.
It's running.
Okay. It's going to go real slow. It's not going to change a lot here, but I just want to point out that let's go to the center image. You'll see red sinusoidal wave. That is the electric field with respect to zero. You see it's at zero. It crosses over zero. That's the electric field as a function of direction, and the direction is determined by these spikes at the bottom there. Each one is at zero. The next one's at 360 degrees later, just like that. So you get a full 360 degrees, and that's the electric field changing around 360 degrees, each one of those loops. So there's actually 1, 2, almost 3 rotations in that center figure going around. You see how uniform the field is. If you look at it carefully, you'll see that the axis is changing down at the bottom. Horizontal axis, time axis, is changing every 3 seconds. So hopefully it's clear enough there. It's actually changing in time. On the far, you don't have to worry about some of these others. Okay, let's go to the lower left. You'll see red and green curves. They're actually changing also every 3 seconds. And they're just showing how well the one sensor and the other, those are two different sensors. They're measuring the electric potential at the ends of that rotating system, and they're symmetric. In other words, when one goes back, it now looks like the other one because once it's rotated 180 degrees, I should get the same answer again because the sensors should be identical. And so I get a double ring, and that's what's showing above in the polar plot. Upper left is a polar plot showing the electric field, and it's a double ring because I'm getting double measurements. Let's go back to the middle here. There are other things here. The green line at the top is noise because I learned that I had to capture lightning. I wanted to catch the light change in lightning, so there's a light sensor on it. There's an upper right-hand corner, there's relative humidity because I didn't know if that was affecting my measurement. At the center line, although I said that was zero, that's not a zero line. See what else do I have in here? Oh, the optical. There's an optical line also. Oh, and here it goes again. This is what it looks like running. It probably changed on you, Missy. You'll see a light image in the lower right, an office.
Correct, yes.
Okay, that's what it looks like when it's running. I'm running this I don't know if I started this one from home or not, but you notice this, it jumped in time, and you'll notice in the upper figure, the polar plot, it's gone small. There's almost no electric field in the room at this time, or in present, the storm had passed. Okay, now, Missy, do you know how to reverse that back up to the middle somewhere? Can you reverse it? So let's say 1 minute, 30 seconds or so, anywhere near there?
I started at 1:30.
Okay, thank you. Okay, let's go to 1:30, and I'll start mine about the same. If you go to the upper right-hand plot, it's changing every 3 seconds, or every 3 seconds. I eventually changed it to every second, but it's every second. This changes every second. And those numbers refer to the electric potential, electric field in that direction. So you identify what the electric field is in that direction, and so the strongest field is in the direction in the lower left quadrant. If the field is coming from the other side of the building, assuming the building didn't affect things, then it would be in the upper right-hand quadrant or other quadrant. So you can identify where the field is coming from just from that information. Okay, let's go to a faster one. No, let's go to 69, chart 69. I was at work when a storm came. It was already raining. And so I turned on my system, and this is what I got during a thunderstorm. I didn't have that capability to store the display in real time, but I was actually screen capture it. And so I'm going to show, this is the data from the screen captures that I got. I have all the data, but anyway, the upper left-hand side shows the electric field during the storm, and you notice it doesn't pass through, it's not symmetric around zero, which is very interesting. And it still created the same oval shape that you saw before in the other images. It still looks like that. It does pass through zero, but it has a greater magnitude in a particular direction. Again, we have the same upper left-hand side, the same 360 degrees repeating. But just before lightning occurred, if you go to the left-hand side, middle one, it separated from, I call it displaced, or it came off of the minimum. It did not pass through zero at that point. And shortly after it did that, I got the next one below, which is the lower left-hand image. It shows the waveform. There was an arcing event, which would be lightning. And you're going to see on the right-hand side is the polar plot of the data for the pre-lightning strike. So the pre-lightning strike data is shown in the pre-lightning strike on the right-hand side. So that's what the polar data. It no longer is going through zero at this point, and then you can see shortly thereafter was the lightning strike, and then it would recover back to the upper left-hand corner again, and it would change shape. And I'll point out now that during a storm, it's like riding a boat. That electric field changes. Sometimes it becomes triangular. Sometimes it gets bigger, smaller, and it rides up and down over the 0 point. But again, the time frame that it does all this is like riding in a boat in the ocean, just like an ocean. It felt just like an ocean wave. Let's go to the next chart, which is chart 69. And I'll look at a couple more charts if you can hold off, everybody. I don't want you to leave yet if you didn't like it, but I'm going to show a high speed of what you just saw. And this is, again, it's after the storm. I don't have it ahead of the storm. I can't make it clear because I had to take several hours and let them compress into something that you can see. But you're going to get to see the system running. So let's see if you could start that one up.
It's running.
And you see that this is the storm leaving the area. You'll see the electric field decreasing. You see the electric field in the polar plot showing the direction, the decrease in magnitude. You'll see the light showing up, the line showing up in the middle here, top middle. That's the light intensity moving up as the thing comes forward, and you see the daytime showing up in the room. Okay, and you can show that again if you want. I don't know. I thought that was, my goal was to get that before a storm, during a storm, after a storm. I just haven't got the IT skills yet to get through that whole thing. I do have, that's X and Y plane. I'm sorry, that's the X and Y plane. I did build an upper right-hand side of this chart. You'll see the Z plane. I did build a Z plane one. I haven't turned it on yet because I haven't inserted the sensors. Where did I get these sensors to make what I think were great measurements for me? I stole them from my 2D array because I could use that as my, I could test 600 sensors at the same time, so I matched my sensors by grabbing 2 out of that sensing system and going forward. Let's go to 71. I was trying to figure out how I would contain that, and I wrote up some work on how to do that. So let's skip that. You'll see that this shows the quasi-static generator. I'm not really in a near field condition because I didn't have a setup to do this, but I'm going to inspect. They were interested in inspecting a moon rock that was contained in a polymer system, and could I look at the dielectric properties of the moon rock in the polymer while it's contained in the polymer system? So I decided I would look at quartz. This is a quartz sphere. Hopefully, Missy, it's running. Yep. Okay, that's quartz sphere. I got very close to the sphere. I'm going to look at data from one point, the closest point to that sphere, which is at the center circumference here, the largest circumference distance. And you can see I'm pretty far away from my uniform electric field plate, but I'm going to call it uniform for now. So I'm taking data like that. I just wanted to show you the complexity. The sphere is rotating. The quartz sphere is rotating also on the left, as well as the quasi-static generator. So I'm taking data every time it rotates. Quasi-static generator rotates around 360 degrees, and I get an increment in change of angle of the quartz that I'm looking at. So if you go to the next chart, this is the result that I got from that. It was very interesting. I'm going to draw your attention to this is chart 73. The quartz sphere is on the far right. It was rotated around 360 degrees, and the gray image in the right side in the middle, that's the unwrapped image of the quartz. And I'm going to go halfway up that image and show the relative permittivity that you measure at the center, going through the center of that quartz sphere. And that's shown in I put in the word draft because I haven't finished it. I would like to validate the results using different methods. And so this is one, I've just gotten to the point that I actually have a number that makes sense and calibrating everything. But this is the one line, sensor number 72, and this is the relative permittivity that I get from that using this relationship here on the middle there, middle left, for the potential that I should be observing outside a solid sphere, dielectric sphere, in a uniform electric field. In this case, I'm using R, the distance from the center of the sphere. I'm using that to be A, the radius of the sphere. So I'm doing it at the surface. So there's a little bit of it should be really an approximation at that point. But I just show some calibration of how I calibrated that sensor to get that measurement. So I'm still working this. And on the lower left, I'm showing you can actually get a 3D rendition if you use that equation there over that angle theta as well as phi. You can get the whole thing, and so you get ER and ER. It almost sounds Chinese. You get ER in XYZ direction. But anyway, this ER here is just notional because I just unwrapped this image here in Photoshop, which allows you to do it in 3D. But you can you get something like that. So that's where I was headed with getting the relative permittivity from systems. So you can, and the goal is to head towards quantitative measurement. Okay. After getting that far, I mentioned that I would like one chart left, I guess, one movie left. This was my last hot off the press concept. I said, well, in space, I can just use the same thing in space for astronauts. So I was talking to my supervisor about it. I said, well, it really would be just like one of those propeller caps with the sensors on it. You can put that on a helmet. And so I set out to do that. I said, well, I can do the same thing for those systems, and I built this system here. This is all cotton. Now, before I start the movie, you wouldn't have this working this way. This could be part of a helmet. It could be a separate system. It doesn't have to be a spinning thing out in the open. It could actually be a rotational system flush with the helmet, and it doesn't have to be. And possibly these solid-state sensors could do the same thing. But this was my concept for a wearable electric field imaging system. And if you can start that up, or if it hasn't started yet, let me know if it started.
It just started.
Okay, so this is it, and don't laugh, but I wanted to make it whimsical. There's batteries in the back. The A is gain. Gain is attenuation, and G is gain. There's a meter. It's going to repeat, or we should repeat it. This is the same polar plot data, except that I've made it all positive because I want to light up LEDs in the hat. So peripherally, the person will know if there's an electric field increase to the left or the right of them, and they can aim in that direction to find out more about it. And it's quantitative, so you get the electric field at that point. The point being, at the top of the, and if you could run that again, Missy, just keep it running. The electric field that you're measuring is at the point, the top of the rotation there, and near real time. I mean, it's real when it's at that direction, but you have to sweep it around. And the meter I tried to, I wasn't sure what kind of sample and hold to use. I just used a basic one. And if you put 2 or 3 objects in there, you'll see those peaks that you see in the waveform. You'll see multiple objects in that peak also. I did not include an oscilloscope view on this, but you could do something like with, folks wanted me to do Google Glass and things like that. But as soon as you start adding polymers and wires and things like that, you start to affect the field that you wanted to measure. So I wanted to make one as pure as I could in terms of measurement, and this is the one that I ended up with. So it's made out of garolite, cotton, balsa wood, and number 38 magnet wires and paper mache and LEDs. I had to put the LEDs, and the circuits are on garolite. They're not on FP4. I can't remember the name. FP. It's not on the regular circuit board. I did it on garolite. And let's see, what else can I tell you about that? When I first wore it, I tried it on myself without anybody watching. The first thing I noticed as soon as I took a step left and right, it lights up left and right that there's charge coming from my feet because I have a rug in my particular office here. And this is just getting ready to be taken out for a test run by some of the junior staff. I don't expect it to come back working, but it's ready to go. Okay, there's some anticipated benefits. Let's go to chart 76. I'm not going to cover these now, other than I think you got a flavor for everything that it can do. And I went to astronaut safety because I got whim of an issue some years ago. It may have been from your group, but I thought maybe this would be interesting in that area. If you go to chart 77, that shows the patents that I have in play on it. I could not give the presentation earlier, which Joe wanted, and I want to thank the prior speaker that was slotted that was going to give the presentation for the slot to let me have this opportunity, because I wasn't going to be able to do it in the next 2 months after that. So I appreciate that, but I couldn't give the presentation earlier because these patents hadn't been set up so I could make a public presentation, and this is public at this point. And let's see, if you go to chart 78, Jesse Midget's the one that's taking care of any tech transfer. I have some folks that are setting up SAAs, and we're working on, I won't go into too much detail on that. Finally, in chart 79 is myself. I was 10 years old, and I was headed for NASA, I guess, at that time, and I'm ready for any questions at this point. I probably went too fast, but I hope you get a flavor for what's going on. Thank you.
All right, well, thank you, Ed. I'll open the floor up for questions.